Welcome to the terminal, everyone. I'm your lead dev for today, and we are diving into a brand new explainer. Today's target, mainframe, Cambridge AS and A-Level Mathematics 9709. Specifically, we are hacking into one of the most notoriously heavy-hitting modules, complex integration. Now, you already know that integration is a massive part of the syllabus, but here's the secret. Knowing the raw math, that's literally only half the battle. Today, we're not just doing textbook equations, we are going to decode the examiner's core mindset, treating this exam like a command matrix so you can optimize your output and secure maximum marks. Let's get compiling. So, we have to start by debugging a massive system failure. Why do students consistently fail at applying integration to unfamiliar contexts? I see this all the time. Imagine a coder. Let's call him Dev Alex. Now, Dev Alex is fantastic at raw data inputs. Give him a standard function in a vacuum and he integrates it perfectly. But the second Cambridge wraps that function in a word problem, like, say, calculating the volume of a specifically shaped manufactured part, boom, system crash, memory leak. The failure rate spikes. You might be wondering, why does this happen? Well, usually it actually isn't a lack of raw math skills. It's a complete lack of strategic application. Candidates simply don't know how to parse the new environment.
Listen to this direct output log from the principal examiner reports. They state point blank that integration is one of the most misunderstood areas in mathematics. This proves we absolutely need to stop staring at just the math algorithms and start reverse engineering the grading methodology itself. The examiners, the people with the ultimate admin rights to your grades, are practically begging candidates to show a deeper level of system understanding. So we are going to fix that right now by looking at the exam completely through their eyes.
Here is our system blueprint for today's explainer. First, Section 1, the theoretical architecture. Then, Section 2, the procedural framework. Following that, Section 3, top examiner warnings. And finally, Section 4, deconstruct, solve, evaluate. Let's execute.
All right, booting up Section 1, the theoretical architecture. Okay, you cannot build a secure application on a shaky codebase. In the 9709 syllabus, your entire foundation is built on 5 core functions. We have e to the power of ax plus b, 1 over ax plus b, sine of ax plus b, cosine of ax plus b, and sec squared of ax plus b. Now, do you notice the syntax pattern here? They all contain that exact same linear inner function. The syllabus framework demands that you recognize this precise architecture. You aren't just integrating e to the x anymore, you need to instantly spot when it's, let's say, e to the 2x plus 3, and know exactly how to manipulate it using the reverse chain rule. If you can confidently identify and manipulate these 5 core functions, you essentially have root access to the entire integration module.
The difference in cognitive domains exactly illustrates what separates standard users from top-tier system admins. Average candidates rely on isolated knowledge. They treat integration like a standalone script. They memorize the rule, apply it to a basic equation, and log out. But Cambridge examiners are testing interconnected systems. Top-scoring candidates seamlessly connect their conceptual knowledge to unfamiliar domains. They bridge integration with coordinate geometry or kinematics without missing a single beat. They don't just know the how, they know the why and the when.
Moving right along to Section 2, the procedural framework. Because listen, knowing the theory is great, but without a strict procedural methodology, your code simply won't compile.
If you take away literally one thing from this entire explainer, let it be this. Examiners desperately want to award you method marks. They are grading your process, not just the final output. The method mark strategy is your ultimate failsafe. In complex high-tariff problems, the final answer is often only worth a single solitary mark. The bulk of your grade, that comes from your processing logic. Imagine you set up a beautiful definite integral. Your syntax is flawless, you plug in the limits, but then, right at the very end, you write 5 minus 3 equals 1. Okay, sure, you lose the accuracy mark, but because your procedural method was flawless and clearly documented, you keep the other 4 or 5 marks. You have to prove your process clearly.
Examiners are constantly scanning your work for a standardized 5-step sequence of systematic processing. First, identify the key elements, like spotting that linear inner function we talked about. Next, apply the relevant integration principle. Third, execute your analysis with abundantly clear working. Do not skip lines of code here. Fourth, verify your results. And finally, present your answer in the appropriate format. If you follow this exact sequence, you are practically handing the examiner a fully optimized, bug-free roadmap to give you full credit.
But even with a stellar process, candidates still fall into hidden system traps.
So let's jump into Section 3, Top Examiner Warnings, pulling directly from the source code of the grading reports.
We've dug through the logs to find the exact places where students are throwing away easy marks. Let me introduce you to another coder, Dev Sam. Now, Sam is actually great at logical loops, but totally fails at syntax precision. And that leads right into these top 3 mistakes. Mistake number 1, confusing cause and effect. This happens a ton in kinematics applications where velocity and displacement are intrinsically linked. Mistake number 2, and this is classic Sam, forgetting format and presentation conventions. I'm talking about dropping the dx at the end of your integral or completely forgetting the constant of integration, the infamous plus c. That is a massive syntax error. And mistake number 3, giving generic outputs that are not specific to the context of the data provided. You have to tailor your response. Before we push this final patch to secure maximum marks, optimize your system feed. Subscribe to Ace the Exams at Ace the Exams right now and turn on all notifications for weekly system updates. Okay, resuming the compile. We just hit a logic error mid-argument. Examiners raise a massive red flag regarding terminology. You must define your terms before diving into complex calculations. Think of it like declaring your variables before running a loop. If the problem asks you to evaluate an area or a volume using integration, make sure you are using the correct mathematical vocabulary when setting up your boundaries. To debug paragraphs that explain your mathematical reasoning, we highly recommend deploying the Peel syntax structure. Point, evidence, explain, and link back to the context. It upgrades your logic instantly and proves to the examiner you are in complete control of the system.
All right, let's transition to our final phase, Section 4, Deconstruct, Solve, Evaluate. This is your ultimate problem-solving architecture.
Let's run this in our interactive beta testing arena. This blueprint is the exact deconstruct, solve, evaluate cycle that separates the A grades from everyone else. First, you deconstruct by identifying the given info and breaking it down into logical steps. Then you solve systematically using those 5 core function algorithms. And finally, and this is the crucial step most candidates skip entirely, you evaluate. You check your limits for reasonableness, and if it's an applied problem, you make justified recommendations based entirely on your numerical evidence. To lock this cheat sheet architecture into your brain, the sources highly recommend building your own memory hack right now. Grab the first letters of these steps and create your own macro. Having a mental checklist ensures that when that exam timer is ticking down and panic tries to set in, you have an unbreakable framework to fall back on. Give it a try right now. Write down those first letters and make a memorable phrase today. Steps 4 and 5 of our process completely rely on this definition of evaluative thinking. It's about questioning assumptions, identifying limitations, and justifying your decisions with hard evidence. This is how you definitively prove your math makes logical sense in the real world. Top-scoring candidates don't just calculate, they evaluate. For instance, if you calculate an area using integration and your output is a negative number, evaluative thinking is what prompts you to halt the compile, recognize that physical area literally cannot be negative, identify the limitation, like maybe you accidentally swapped your upper and lower limits, and correct that assumption before moving on. As we log out of today's explainer, I want to leave you with this final, absolutely crucial thought. If Cambridge examiners award the most marks for the process, are you just chasing the final answer, or are you clearly proving your method? Every single time you run an integration pass paper, ask yourself, am I making my method undeniable? Are my steps clear enough that an examiner has no choice but to award me the marks, even if I fumble the final digit? Shift your focus from the final destination to the algorithmic journey. Apply the theoretical frameworks and systematic processes we've covered today, and you will absolutely master the 9709 integration module. Before you go, make sure you optimize your system feed, subscribe to Ace the Exams at Ace the Exams, click that notification bell, and leave a comment down below with your subject and level so we know exactly what to target in our next patch. Keep practicing, keep evaluating your code, and I'll see you in the next one.